All right, so welcome back. We have just derived our surface area formula for the area for some volume of a solid revolved either about the x or the y. Of course, right now this is currently stated in the language of x. If this was a volume that we were dealing with moving up the y-axis, then of course these would be functions of y dy. So let's consider our process with an actual cone, which we can actually find the volume of. If you look up the volume formula of a cone, I actually have one in my textbook, not volume, but surface area of a cone, it actually gives that pi RL function, okay, for the surface area of a cone. So the one that we developed earlier, pi RL, that formula still works. And so let's say in this example, we're dealing with a cone that has so we want to do surface area of a cone with radius 9 and height 3. So we can actually model that as a straight line that's been revolved about the x-axis. Okay, so model that as a straight line that's been revolved about the x-axis. So since it is a full cone, it starts right here at 0, 0 and continues over until you get the point x equals 3 and y equals 9. Okay, so that means that the slope of this line has a rise of 9 compared to a run of 3. It has y-intercept at the origin, so the equation here would actually be y equals 3x. Okay. So on the one hand, if we do this just with the surface area formula that's given for a cone, which is just pi times the radius times the length right along the long side, then we would get pi times the radius, which is 9, times L, which is the hypotenuse of this right triangle. That would be square root of r squared plus h squared. And when we work that out, we get 268.23 square units. Okay, so that's the actual surface area found using the surface area formula that you can find for a cone. Now, again, which is actually the same one we used in the derivation of the formula we eventually come up with. But now we're actually going to use the surface area formula. So we're going to use surface area integral. So remember that says the surface area is the integral from a to b of 2 pi times the function times the arc length. Dx. Okay, and so let's do that now. Let's do that. So our function was y equals 3x. So y prime would just be 3. So plugging that information in, we would have the integral from 0 to 3 of 2 pi times 3x times the square root of 1 plus 3 squared dx. Okay, and then we just start to simplify. We can put the 2 and the 3 together along with the pi and this square root of 10. All that stuff can actually be brought outside. So 6 pi square root of 10 integral 0 to 3 of x dx. And then we integrate. Add 1 to the exponent makes it x squared. Divide by it. 2. I'll do that on the outside. That'll be 3 pi square root of 10 x squared. Evaluate it between 0 and 9. Okay. Or sorry, 0 and 3. When we plug 3 in for the x squared, it'll become 9. So then we work that out. We plug in 3 pi times square root of 10 times 3 squared. Right? And that'll be minus 0. And what you will find when we do that, 3 times x squared, 3 times 9 times square root of 10 times pi, we get our 268.23 stuff that we did before. Just kind of confirming that, yes, this does agree with the formula for the surface area of a cone, which it should, right, which it should agree to, since it was derived from that. This is just an example to see how this formula works with a pretty easy function. And so we're able to compute that pretty easily. And just to kind of see how surface area works. We'll look at some other functions, maybe a little more complicated ones, in the upcoming examples.